On January 5, 2020, a black hole 9 times the mass of the Sun collided with a neutron star. The event, cataloged as GW200105, produced no flash of light and no glowing debris. The neutron star was likely swallowed whole by its partner. This collision was only detected because it sent ripples through the fabric of space-time that hit Earth 900 million years later. They were picked up by LIGO, the Laser Interferometer Gravitational-Wave Observatory, which uses specialized detectors to measure the infinitesimal stretching of space caused by passing waves. For decades, astrophysics has relied on a specific expectation. As dense objects spiral together over billions of years, they radiate energy and their orbits gradually smooth out into near-perfect circles before they finally merge. This assumption became the foundation for gravitational wave astronomy. Scientists built their mathematical models to search for these circular death spirals, assuming the universe naturally corrected any irregularities long before the moment of impact. But when the signal from GW200105 was processed through these standard models, the math didn't match the observation. The data revealed systemic errors that the circular models couldn't resolve. The masses were skewed. The models calculated a black hole that was too light and a neutron star that was too heavy, creating a physical profile that contradicted previous observations of these stellar remnants. For physicists, this was a crisis. These mass estimates made the merger appear to defy the behaviors predicted by Einstein's equations of general relativity. If these figures were correct, our primary framework for describing gravity was failing to explain the most extreme events in the cosmos. A single assumption about the shape of an orbit was making the laws of physics look broken. Researchers at the University of Birmingham realized the problem might not be the physics, but the lens they were using to view it. They moved away from the standard models to test a more complex hypothesis. They replaced the standard circular models with 5-dimensional eccentric models to measure how stretched an orbit is. This oval path causes the objects to accelerate and decelerate, generating complex mathematical harmonics completely absent in a circular signal. This chart shows the signal-to-noise ratio of the event data compared to the expected background noise. When the GW200105 signal was compared against thousands of eccentric templates, the model successfully tracked the data points highlighted in orange and yellow. The analysis isolated the event from the background triggers. In this visualization, the red diamond representing the merger stands clearly apart from the blue cluster of standard circular injections and the black noise triggers. By adding that 5th parameter, eccentricity, the true nature of the collision was revealed. In data analysis, forcing the wrong model onto a signal creates a false positive, an error that looks like a discovery. By forcing a rigid circular template onto an oval reality, the researchers inadvertently corrupted the readings. The broken physics was actually just a mathematical artifact of the wrong assumption. Once the eccentricity was factored in, the mass estimates shifted back into their expected ranges. The data aligned with general relativity once again. The laws of physics hadn't changed. We simply had to look at the shape of the orbit to see how they were being applied. This discovery created a new question for astrophysics. If these systems naturally circularize over millions of years, why was this pair still moving in a stubborn oval at the moment they merged? Most binary systems evolve in isolation. In the empty void of deep space, they have nothing to disturb them, allowing their orbits to slowly smooth into perfect circles. Because GW200105 was still moving in a stretched oval when it merged, we have strong evidence that this pair was never isolated. The lingering oval shape is a physical record of the turbulent gravitational interactions that shaped the system's history. The system likely formed in a globular star cluster, an environment where millions of stars are packed together. In these dense nurseries, objects are constantly passing close enough to tug on one another. Every time a third star passed near the binary, its gravity knocked the pair into a more elongated, chaotic path, preventing the orbit from ever becoming circular. Future observatories like LISA, the Laser Interferometer Space Antenna, will be located in space to detect these signals with even greater precision. They will rely on massive libraries of eccentric templates to identify these chaotic signatures. Scientists can now read these waves to map the exact environments of the nurseries where black holes are born. By decoding the shape of the wobble, we are finding the most violent corners of the universe.